Hi everyone, I hope you are all safe and sound. This is actually the Recitation 11, which was supposed to be held on April 24th and April 25th. We will be solving question 2 on exercise set 10. It's only one question, but it's kind of long. So let's start the question. Capstan system. We consider a capstan that has 5 cabs or taxis as members. When a passenger arrives to the capstan, the next cab in the idle cab sign takes the passenger to a random destination in an exponentially distributed amount of time with a mean of 10 minutes. After delivering the passenger, the cab returns to the cab stand in an Erlang distributed time with shape parameter k and scale parameter 7 in minutes. The parameter k is also known to follow the PMF px equals 0.2 for x equals 1, 2, 3, 4, and 5. The cabs that return to the capstan get in the idle cab sign adopting a first in first out policy. So we have a cab sign taxi line, right? On the other hand, if arriving passengers do not find any cab in the cab stand, they get in a line and wait for cabs to return to the cab stand. So we also have a passenger sign. Q. The passengers are patient, do not vanish, and do not carpool, and adapt to FIFA rule in the waiting line. So part A says that. Assume we have observed the arrivals of passengers to the cab station between 8 a.m. and 8:30 p.m. The data of interarrival times in minutes can be found in exercise set 10 Excel file. Analyze the data using several visual descriptive statistics to decide if it is safe to use Arena's input analyzer to identify a statistical model for the data. So let's open the Excel file, which was supposed to be this. Okay, this is our data in column A. We have 100 points in our data. So we're actually seeing, we will look at the data to see if the points in data are independent from each other. Okay, so we have to look for these parameters, the minimum, maximum, mean. So with that, we can see the range of our data. So the minimum can be found by the min function, and the maximum is 19.490. So we can almost say that our maximum is 20, right? So our range is like 18 point something. So I can split this data in square root of n bins, right? So the ideal bin for my data would be square root of 100, which is 10 bins. So we have 10 bins here, and what should be the intervals for my breaks for bins? We can find it by range over. So this is my range. So assume that my maximum value is 20. So 20 over 10 is 2, right? So my breaks can be in increments of 2. 2, 4, 6, 8, up to 20. Okay, now I want to see how many points in my data fall into these bins. I can find that using the frequency formula. I think it's not written in here. The frequency, and you just choose your data array 1 to 100, and after you choose your bins array, like from here to here. The resultant list is given here, and we will be using histogram to see which distribution can be represented which distribution can represent this data, right? So when we use this histogram, you can insert the histogram by first selecting the data and then come to insert, and you have those several graphs here. So you can create 3 of these graphs from here. So the histogram kind of looks like a right-skewed normal distribution, but obviously it's not normal distribution, but it's right-skewed, right? So we can say that gamma, Erlang, and Weibull distributions can be used for this kind of visual here. So already Erlang exponential chi-squared are special cases of gamma distribution, and Erlang is like almost same as gamma, but we have the shape parameter as an integer. Okay, so when we do this scatter plot here, maybe when you see this lag one, it might be kind of familiar to you because we saw that at the very first weeks of this course, where we were looking for the independence among random numbers, right? So in here, you can also create this by coming to insert and choose scatter plot here. So in here we are comparing the kth versus k plus first observations here. The scatter plot shows, if there is one, the autocorrelation. If there were like a point clustering along a line, like going down or coming down along a line, it would mean there is a high correlation. But in this case, we have this random scatters. So it means we have no significant autocorrelation in our data, which is a good thing, right? And also, when we look at this plot diagram, which you can also create by coming to insert and choose this 2D line here, the tolerance going from, so we have this mean here, right? We can calculate it with the formula average. From this mean, we are deviating as much as the standard deviation, so it's kind of pretty stable. So we say that interarrival times always deviate around the same average with a constant variance. So our parameters of the statistical model are not time varying. So looking at 3 of those plots, we can say that it's safe to use the arena input analyzer to identify a statistical model for the data. Okay. Actually, at first, I have to create an arena model. Okay, let's start the model. I come here and okay. In our question, we have cabs coming in the morning and we have passengers arriving in the system, right? So we have actually 2 different entities in the system. Let's start it with, let me just zoom this. And okay. Let's call this passenger arrival. And entity type is passenger. So this, according to, okay, let me just see the question again. Okay. For the B part, we should be using Arena's input analyzer to identify a statistical model for the data, because using this data, we will be seeing the interarrival times, the distribution for interarrival times. So that's where I was confused. Let's come here. So in order to see the input analyzer, let's close this. We have tools here, and you just click on input analyzer, okay? And then you see this window here, and I click on this to open a new window. I click on file, I click on data file, and use existing. Now, I have already downloaded the interarrival times from LMS, and you can also see it at the exercise set 10 part. But if you cannot download it, by the way, just click on it, open the file, and click on Control plus and S. So Control S to save the file, okay? Now you have a TXT file in your computer, but Arena only sees these DSD files, so you should change it to text files here so I can see my data, okay? I open my file and you see these values here, which we already did in Excel, right? So I come to fit and say fit all. Okay. This is an important part of input analyzer. So we try to reduce the estimation error when identifying the distribution. Our goal is to obtain a reasonably good approximation because so we already checked if our data is good enough or good to use for input analyzer, right? We already did this, but if we didn't do that, when we use this input analyzer, the Arena gives us the best fit among several distributions. So the best fit may not be a good fit. For example, the best fit may have the minimum scared ever among all distributions, but it doesn't mean it's a good fit. So we have to check the p-value, don't forget that. And a large p-value tends to indicate a good fit, and a small p-value suggests a poor fit. Okay, now we set that fit all. It says the best fit for our data is Erlang with parameters 2.49 with shape parameter 3. Okay, so you see that our square area is pretty small. It's 0.0038, something like that. You can check minimum scared error versus variance, and if like it's the conventionally used way, if the minimum scared error is much smaller, then you're good to go. You should drag it to 0 as much as possible. Okay. Now you also see that our corresponding p-values are also high, right? Higher than 0.05. Okay, now we see that our best expression is this. We will be using this for our model in Arena. Okay, now we have to redo this again. Let's say passenger arrivals. Because the C-part says that assume the statistical model you have identified in B for the interarrival times of passengers, run the simulation for 100 independence days, which means replications. Each day the cabs will work between 8 a.m. and 8:30 p.m. hours. For the sake of simplicity, all 5 cabs will be waiting in the cab stand at 8 a.m. and the replication will immediately terminate at 8:30 p.m. without observing what will happen to the passengers who are being served or waiting in a line by time. We assume a warm-up period of 30 minutes and answer the following questions. So we have several questions. Let's model our question here. Let's say passenger. Our type is function airline and point 49, which we found in input analyzer, and units is minutes, right? Entities per arrival is 1 and maximum arrival is infinite. So the first creation is same with our expression, right? Because we are using the inter-arrival times for the passengers. For example, if my for my first passenger, if my inter-arrival time is 3, then my first passenger will come at like 3 minutes after the simulation starts, right? So that's why we are saying first creation is this. Okay. Now we also have caps. Let's click on this and say caps coming in the morning. Entity type is cap, and let's look at, so in question it says that 5 caps are coming, right? Let's look at the question again. We consider a capstan that has 5 cab taxis as members. So the reason why we are not using these taxis or cabs as resources is that these cabs are okay. I think an earthquake happened. Okay. These cabs are also coming into the simulation each day and being used, and after it drops the passengers comes back to the queue, right? They are also an entity. Type is constant. Value is 1 and is minutes. Entities per arrival is 5 at each morning. Okay. Now, the point is, we have passengers and cabs, right? So we have to match these passengers and cabs somehow. So we will be using match and batch modules in this question. Okay, let's click on match. So it's at advanced processes. Let's say match passenger and cabs. So what is the match module? It's just it kind of synchronizes cabs and passengers, so that can be paired before we batch them. So we use batch module to put together different types of entities in one unit so that they can be processed together. So in order to be processed together with batch, we at first match them. So you will see at the simulation there will be a cab line, cabs line, and a passenger line, and it will be like the cabs will be waiting for the passengers, and then they will be both synchronized with matching attributes. So at the batch module, it will combine a fixed number of these entities so they can be processed together. Okay. So let's say number to match is 2 and type any entities, no batch action. Okay. So you see that since its number to match is 2, we have 2 lines, right? So let's go to basic process and queue. Yes, it's first in, first out for both of them. And also let's connect these two. Where is batch? So batch is also at the basic processes. Okay. I want this to be. I think it doesn't matter where. Okay. Now let's connect match and batch together. They will be both going to batch. Okay. Let's click on batch and say batch passengers and cabs. So the best side is still our save criterion is lost and our type is temporary because after the process of like the passenger transfer, which means we will be taking a passenger which we matched and batched with these modules. We will be taking them to a destination, and after that happens, we will be separating the passenger and the cab, right? So it won't be, this batch won't be permanent. So I click on temporary. Representative entity type is cab. Okay. After that, let's click on this. Is also FIFO as well, default. Let's click on basic process, and now we have the transfer, right? We took our passengers as taxis. Now we will be dropping them off to a random destination. So in the question it says the cab takes the passenger to a random destination in an exponentially distributed amount of time with a mean of 10 minutes. So let's plug this into the model. Okay. So we don't have any resources in this, right? We just have an entity consisting of two entities. So we have a batch, and our action is delayed because we have no resource to seize and release, right? This process only takes a certain amount of time, so the action is delay. Our delay type is expression, and it's a minute. So let's say build expression here, and say random distributions is exponential between 10. Okay, so mind that we are clicking on this report statistics. Let's connect them. So after this, okay. Anything missing? No. After this process, after I drop my passenger to the random destination, right, we have to split this batch. So I come into this and choose separate. I say separate destination. And say split existing batch, because after I'm done with my taxi, I'm just departing from the simulation, from the model, right? But after the cab drops off its client, it have to go back to the line. So we have to separate this batch into two. The member attributes are, yes, retain original entity values. Let's say okay. So in order to a passenger to depart from the system, I have to decide if it's passenger or not, because coming from this module, the separate module, we have two different types of entities, either cab or a passenger. So I have to decide if it is a cab or a passenger. Click on this and let's say also it's not separate destination, it's separate passenger and cab. Okay, so this is a two-way by condition. If my entity type is passenger, depart the system. Let's call this separate destination. Okay, if yes, depart the passenger. Okay, let me check the magnitude of the earthquake. Okay. Now, if false, which means if it is a cab, then it means it's a taxi, right? It's a cab. So, looking at the question again, we have a cab returning process. After delivering to passenger, the cab returns to the cab stand in an Erlang distributed time with shape parameter k and scale parameter 7. So we are giving to PMF. So let's put this into our model. We will be using this process here and connect the false part of the side module with the beginning of process. Okay, it was 4.5 magnitude. Okay. Let's connect the end of this process with the beginning of, let me do this, match passengers and cabs, because after the cab is done with its passenger, it will go back to the cab line and it will be waiting for another passenger. That's where it waits for to match with the passenger. Okay, let's say here cab return process. And it is also delay, right? We have no resources. Same with the previous process. Our delay type is expression. Units is minutes. And expression is random distribution. Is Erlang same with K? I guess. Yes. So, let's look at the question again. It says, the parameter K is given like this, and we also have, okay, this is our shape parameter, which is put in the arena at the second after the comma, right? My scale parameter is put at first, so I have to put 7. Let's come back to arena again. 7. So after this, my Erlang parameter has a PMF. So I already showed you this in my previous recitation, and I am pretty sure that you saw this in lectures. When we have a discrete CDF, we do like this. So with 0.2 probability, my x is 1, and I keep adding these probabilities up, right? For each of these x's, 1, 2, 3, 4, and 5, my probability is 0.2. So 0.2 plus 0.2 is 0.4, and it is for x between 1 and 2. And 0. Not point, like, yeah, point. 0. Actually, let me put this like the 3. Let me fix this fast. Okay, with 3 and 0.8, comma 4. So the remaining with 1 probability is 5, right? Since it is a CDF. Okay. I built my expression. It's the minutes. I clicked on report statistics. Okay. So this is pretty much our model. Let's check the entities with our spreadsheet. We have passenger and a cab. Okay. Also, okay, I will show you the pre-existing model so we don't have to deal with the run parameters from scratch. Let's check the queue spreadsheet. Yes, we have these 3 queues. For the match module, we have a passenger line and a cab line, and we also have a queue for just one queue for a cab waiting for a passenger, and passenger just hops on the cab. Okay. Let me open this. Not here. Downloads. Wait a minute. Let me check. Okay. It is zipped, so that's why it doesn't. Okay. File. Open. Capstan system. Okay. So I click on run and say setup. And these are my replication parameters. Our number of replication is 100. So this number of replication is important so that we have a high precision, right? Our warm-up period is like 30 minutes. Was it like that? Yes. The warm-up period is 30 minutes, so that's why we are plugging in 0.5 hours, and replication length is 12.5 since it's going from 8 a.m. to 8:30 p.m., right? So, but my base time units is in minutes because I want to see the results in minutes. Okay, so when we run this, let's run this model. So you see that there is a passenger line here and a cab line here, and those after they are synchronized, we are batching them. So we're not exactly putting together these two entities together here. We are synchronizing them so that they can go to the batch module to be put as one entity. Okay, I want to see the results. So the first question in part C is, let's look at it. What is the average waiting time for a passenger in the queue? Provide 95% confidence interval. Okay, this is my main report. I have all of these results here. So it asks for average waiting time for passenger in the queue, right? So I have to look at queue. This okay. So in queue, average waiting time for passenger in the queue. So this is my passenger queue, and we have this cab queue, right? So this is my average waiting time for passenger with my half width 0.85. So we have to say this plus a negative 0.85. This is my margin of error, and it is also called the precision. And by the way, Arena reports 95 confidence interval half width on this report. Keep that in mind. So the second question is maximum time that a passenger has waited in the queue in this 100 days. For over these 100 replications, I want to see the maximum time that a passenger has waited in the queue. Right? So I have to look at this maximum value, not the maximum average, maximum value over this 100 replications, which is 83.59 minutes. Okay. Third question is average value of maximum waiting time for passenger over 100 days. So now we are looking for this average value. So out of this 100 maximum values for 100 replication, I am looking for, okay, let me clear just what I said is I just messed it up, right? So out of this 100 replications, we have the max average values. We are now looking for the maximum one. So this is a 19.643. Okay. The third question is, okay, we already did that. Average waiting time for a cab in the queue. What is the average time for a cab in the queue? Provide a 95% confidence interval. So now we are looking for the cab queue, and our average is 7,3544, etc. And our confidence with 95 confidence level confidence interval. Oh my god. My half width is 0.52. This is my margin of error, as I said before. So it's plus negative 0.52. What is the maximum time that a cab has waited in the queue in this 100 days? So again, over 100 days, I am looking for the maximum time that a cab has waited in the queue. So I have 100 different waiting times in queue for cabs for 100 days, right? I'm looking for the maximum one out of this. So it is in here because it's my cabs queue, and this is my maximum value out of 100 days. Other question is, what is the average value of maximum waiting times for cabs over 100 days? Okay, now we're looking for the average value of maximum waiting time. And we can find it here is, again, maximum average here is 13.47, etc. Mind that when you are looking to averages, you have half widths, but these are just like single values, maximum average and minimum average. But with averages, you have also these tolerances, right? Okay. What is the average length of passenger waiting line provided 95% confidence interval? So it's asked for now the length of passenger waiting line, right? So we are looking for, again, queue and number rating. At my passenger sign, the average is 0.68 with margin of error of 0.12. So 0.68 plus a negative 0.12. What is the average length of cab waiting line? So we looked for passengers and now we're looking for cabs. Is just below the passengers, which is 0.91, right? With my half width plus and negative 0.06. Again, half width shows the precision, right? I would want a like a sufficiently small confidence interval. So I would want the half width to be small. Okay. Now, if the last question is, what is the observed maximum number of passengers in the queue in this 100 days? So I'm looking for the observed number of passengers in the queue, which is our maximum value here, and is for the passenger line. So that's it for our recitation 11. If you have any questions in Turkish or English related to this question or anything else in the course, we are ready to help you. You can mail us and come to the office hours, and I hope you are all safe and sound again. Goodbye, and see you at the next recitation.